Oh, wait a second. Where'd the chat go? Oh, that's right. They changed Zoom. Shoot. Oh, man. Oh, there we go. Okay. We play a game I like to call old people using computers. Except I hope I'm not that old. It's always so funny. I was, how many meetings do you guys have in Zoom? It's like, is this working? Like, all right, I'm doing this. Can you hear me? Okay, where is this thing? Okay, Paul, how do you do that? That's like the story of my life. Like, all right, this is why I do several things at once. So sorry if I was playing old people using computers. I just did an update for Zoom. So they moved everything around. I had to figure out what the chat was. So this episode of Old People Using Computers is brought to you by the UH Regents. So anyways, so I think this will be our last lecture of content. Next week, we'll do some reviews. So hopefully you feel better about chemistry because we're easing our way in. So like that way you're not feeling super high stressed. So would you guys, anybody have any questions? I emailed you, but I thought of your question. So the question last time was, does dark energy affect bonding in any way, shape, or form? And I thought about it a little bit more, and I mean, so it's hard to answer, first of all, because we don't know what dark energy is. So, but I'm going to make an analog to gravity and say, if you look at gravity and how gravity affects bonding, basically gravity doesn't affect bonding whatsoever, unless the gravitational field is very, very strong. So if it gets really, really strong, certain things can happen, like release of potential energy, and it can heat things up, and then that can break bonds. Or which we'll talk about soon with stars, you can have even nuclear fusion happen. It just breaking down other types of degeneracies. So like meaning the when you have positive and negative charges, if you push things hard enough, things can happen. And that's, so I'm going to make the leap and say, perhaps there's something similar with dark energy, where if it gets really strong, there's some end of the world, end of the universe things where we have the great rip, where eventually dark energy puts the velocity of the universe so high that it tears apart space-time and things like that. So well, that's my initial answer, or I guess it's a secondary answer to the question. Does anybody have any other questions? Nope. Okay. So we are in nuclear chemistry, and surprisingly enough, especially today's lecture, it's going to be kind of apt because we're going to talk about nuclear power and nuclear weapons. And I mean, those things are on the forefront of many people's minds. So also, I'm trying to decide what article to send you guys out, because I always send an article every week. There's a really cool one on radioactivity, and there's been some other advancements going on in COVID. I've been saving some articles, and the Japanese, they just came up with a protease inhibitor. Well, they didn't just come up with it, but they have some data that came out on their protease inhibitor, just like the Pfizer drug. I forget the name of it, like Plaxid or something like that. I want to say but anyways, I'm trying to decide, well, I'll ask you guys, which one do you guys want? You want nuclear, or do you want COVID drugs? Nuclear, okay. It's about cancer treatment. So it's tying things to, okay, I'll send out the nuclear one then. I'll save the COVID drugs for next week. Oh, besides what, did you hear that Fauci said that the pandemic phase is over in the United States? Yep, we're no longer in a pandemic. So, but I think everyone kind of realized that already, though. It just takes a while for people in charge to say, guess what, we're not in a pandemic. So we'll see. So, okay, so we're in nuclear chemistry. And this is where I left off. I talked a bit about radiation and different types. So, and how things decay. And radioactive nucleus, it's one where it's unstable. And things, and things move towards more stability. So very, very massive nuclei, they will decay down to smaller ones. And also if there's the wrong ratio of protons and neutrons, then other things can happen. The neutrons can decay to protons and electrons, and then the protons can either emit a positron, or they can do an electron capture, where it takes the electron, usually in the 1s orbital, and the proton becomes a neutron. So, and whenever that happens, gamma rays are produced. So, and one of the very common applications for radioactivity is dating things. So there's a couple different types of dating. It depends on which radionucleotide we're looking at. This one here, we're going to look at carbon-14. And there's other types. There is uranium-238 and also potassium-40. So if you know the age of the Earth, it said it's 4.6 billion years old. And you wondered, how do we know that the Earth as a planet is 4.6 billion years old? Well, we look at the ratio of uranium-238 to lead. I think it's 262 is the isotope. I'm not entirely sure though, but look at the ratio there. We get the 4.6 billion years. Same thing with, and using the same math with potassium, we can date it to also 4.6 billion years. So we have two independent radioisotopes. So dating things, we can date geological features by uranium and potassium. And other things you can date, so you can date wines with tritium. So, I mean, for me, I go to Costco and buy wine, I'm not gonna pay someone to date the wine, but maybe if you have as much money as Elon Musk and you like to have wine and you want to have someone date your wine, you can do that. But I'm certainly not going to do that. With my drinking habits and my budget, I should say. So, but with living creatures or things that were living, so you can do radiocarbon dating, and the idea with this is, well, carbon-14 is radioactive. So carbon has three general isotopes. There's carbon-12, which is the majority, and about 1% is carbon-13, and then a trace amount of carbon-14, which is radioactive. And carbon-14 usually comes from from the sun. So radiation from the sun takes nitrogen and knocks out one of the protons, and it can turn into carbon-14 just from radiation from the sun. So there's a little bit of, because of the sun, there's a little bit of carbon-14. And the idea is that carbon-14 then turns into carbon dioxide as uptake by plants and to form glucose. Animals eat the plants, and more or less all the living creatures here on Earth tend to have about the same amount of carbon-14. So when you die, or when plants die, they stop photosynthesizing. Animals stop eating plants and other animals, and then their carbon-14 start to decay. So if you know the ratio of the original carbon-14 to the no longer living sample, you can get a general idea of how old something is. Now, mind you, this has changed, so this won't work for us. So the reason for that is for two reasons. Nuclear power. Nuclear power generates a little bit of carbon-14. And the other thing that generates carbon-14 are nuclear weapons. So, and as of I'm recording this video, Russia has not used nuclear weapons in the special operation, so it claims, in Ukraine. And a lot of people are afraid about radiation from it. And one thing about nuclear weapons, we have detonated over 2,000 nuclear weapons. So for testing, we've only used 2 in warfare, that's the United States used in Japan, but we have detonated over 500 nuclear weapons in the atmosphere. So, and that has generated a lot of carbon-14 and also other radioactive isotopes from the fallout from those. So if there are a few bombs that go off, it's going to be okay. And I hope my soothing words there are not needed. And I hope we do not have this escalate to nuclear events. But you can see, though, we have blown up over 500 nuclear weapons in the atmosphere. So we're going to be okay. So, and I mean, that was over years versus a short exchange, but I mean, it's going to be fine. I mean, United States, for instance, I mean, you know that we have a tenuous relationship with Micronesia because we dropped, I think it's 65 nuclear weapons in Micronesia. So that's one of the reasons why we just bombed the heck out of them with our nuclear devices. So, but, you know, so it'll be okay. I mean, again, I don't want this to happen. We can talk more about nuclear weapons later. So carbon dating won't work for us, especially if you were to date us and versus our parents would look like they're much younger than we are, and we would look a little older compared to our parents because our parents are more radioactive. So because they were alive during the airborne testing of nuclear weapons, whereas the last, at least, well, I guess North Korea blew one up a couple years ago, but that was underground. So it's been a while, I think since the 60s, since we've had an airborne nuclear detonation. So, but anyways, so let's look at this. A skull is believed to be an ancient human and has a carbon-14 decay rate of 4.5 disintegrations per minute per gram of carbon. If living organisms have a decay rate of 15.3 disintegrates per minute per gram carbon, how old is a skull? So the way that they do this, they take the carbon of whatever it is they're looking at, like Dead Sea Scrolls, skulls, and then they basically isolate out the carbon, and then they either by powder or by carbon dioxide just burn it and get a big balloon full of carbon dioxide, or they just use a powder and then they look at just how much radiation is coming from it. It's real easy to find radiation. So like with using a Geiger counter. And then you relate it to what you know, and then you can get the years fairly accurately, or at least a general range. So another thing with radioactive decay is its probability. It's actually just plain old probability. And but when you're dealing with a huge number of things, probability tends to follow a pattern, and it's first order kinetics. So, and so like almost everything, banking interest, most chemical reactions, radioactive decay, it's all first order kinetics. So you can use the first order integrated rate law, and you can solve it for, so then natural log of the concentration at some time over the initial concentration is equal to minus K, the rate constants, times time. So if you, so how do you do this? I'm on the wrong page. So you want to solve for time. So then time is equal to ln, well, I should say minus ln AT over A0 over K. And your question is next is, what is the rate constant for this? So half-life, if you remember, is the natural log of 2 over K, which implies K equals the natural log of 2 over the half-life. And this is all, if you remember, this is all from the kinetics chapter. Sorry, I'm trying to, yeah, let me Everything's wobbly for some, I don't know. Here we go. Okay. And so then time is going to be minus the natural log of AT over A0 all over the natural log of 2 divided by the half-life. And just my brain right now wants to go ahead and take this, because you divide it, just bring it up. Oops, not the divide. Because when you divide by something, the thing comes up. And you plug in the numbers. So even here, if you want, you can distribute the minus and put the A0 on top. I'll go ahead and do that. So ln A0, it is 15.3 all over 4.5. So if you see, I'm distributing the negative. I can do this now. If you distribute the negative, you flip this fraction. So it becomes A0 over AT. That's one of the rules of logarithms. So actually what I should do is move this over here. And the half-life is 5,000 years. Where is it? Oh, it's right there. I wrote it down. 5,715 years divided by natural log of 2. And you put that on your calculator and you get 10,000 years. So that skull is 10,000 years old. So recap for this one. Radioactivity is a first order process. It's, like I said, it's probability. And when you have probability with a large number of things, it almost always turns out to be first order. And so like I said, most things are first order. So you can use the first order integrated rate law. The natural log of the concentration of whatever at some time is equal to minus the rate law or rate constant times the time plus the natural log of the initial concentration. We can, by the fact that the half-life of the reaction is known, we can solve for the rate constant being the natural log of 2 divided by the half-life, and solving for time is going to be minus the natural log of the concentration of some time over the initial concentration divided by the rate constant. We can plug in the rate constant is natural log of 2 over T1/2. So that brings the fraction, the half-life on top of the fraction, and then the numerator, and then distribute the negative sign to flip the fraction in the natural log. So half-life times the natural log of the initial concentration over the time at concentration, whatever time. That the thing divided by natural log of 2 is the amount of time, and we get 10,000 years. So it's just an application of the first order rate law. Questions with that? Yeah, go ahead. So you can use this identity, minus ln A over B is equal to the natural log of B over A. So that's just an identity. And if you're wondering why, because natural log of A divided by B is equal to natural log of A minus natural log of B, right? So, and if you multiply this times -1, this equals natural log of B minus natural log of A, which is equal to ln of B over A, which, is minus ln, which is, comes back here. So it's just, -1 times that is the same thing as flipping the fraction because of this identity. So sorry for the trig proof in the middle of a chemistry lecture. Other questions? Okay, not in the textbook. The way that that we model nuclei is sort of like a water droplet. So think of a liquid droplet, like something like water or oil or something like that. And imagine you have this droplet, and then you take it and you drop another, like a smaller droplet into it. So imagine that. So imagine you're in space, in like the International Space Station. You have this big blob of water, and then you go and you shoot a little squirt of water into that. What's going to happen when you do that? The sphere of water is going to kind of wobble. It's going to kind of, if it absorbs the water, it's going to kind of wobble, and then it can break apart. And then if it breaks apart, you can have you can have two big droplets, form. It can form in two. It can break in half, and then little droplets fly off too, and kind of thing. And that is how nuclear fission works. So nuclear fission means to divide. So when something fizzes, when you have a fission, you mean a division. And then there's a fusion. We have nuclear fusion. Fusion is when you take two things and you form it together, two or more things. So when you get a bone fusion, so if you want a bone fusion in your neck or in your back, they take your vertebrae and they stick them together. So that's a bone fusion. And when you have a fission, then that means that things break apart. And I'll show you the chart later about fission and fusion. But when you have fission, and the fission the things that fizz, they tend to be the ones that are bigger. So especially past iron, and even more past lead. So and the way that they fizz is that you have to have this droplet. You have this droplet of protons and neutrons, and it's just like a fluid. And you absorb another nucleon, and then that excites the nucleus. And I mentioned before, gamma rays is one way that you can decite, just like electrons. Another way that things can decite is by breaking apart. So nuclear fission is a way to decite an excited nucleus. And the products also from nuclear fission, they follow a general trend. So there's a mixture of products, but they're fairly predictable. And there are another thing also not mentioned in the book. There's something called the pairing energy. So neutrons and protons work just like electrons. They occupy orbitals, and they are spin up, spin down. So for electrons, the pairing energy is so low. Actually, when you pair electrons, it emits energy. I shouldn't say E, it'll be capital E. So with this is specifically called pairing energy. And there is actually a great deal of stability with being paired, having two fermions like protons, neutrons, and electrons, having fermions paired. So for the most stable nuclei are always the even numbered. So, and the reason is because of the pairing energy. So even when you have nuclei that are even, those tend to be very, very stable. There's very few odd nucleon stable nuclei. I think it might only go as high as nitrogen. I mean, it's really low. It's really, really low how many odd protons, odd neutrons. It's almost always even neutrons. I mean, you can obviously have odd protons, but if there's odd protons, it's, with very few exceptions, it's going to be even neutrons. So when you have something like uranium-235, So the nuclear fuel is going to have an odd numbered of neutrons. So like 239, plutonium 94. So this is what we generally use in nuclear weapons is plutonium 239. And notice the same idea. It has an odd number of neutrons. So even number of protons, odd number of neutrons. And so what happens is a neutron is added, and this has to be what's known as a thermal neutron or a slow neutron. So that neutron is added to the uranium atom, and then it pairs up, and then it excites. This is an excited nucleus. So, and what happens to excited nucleus? It breaks apart. And so just imagine this droplet that absorbs a neutron, then this energy is released, and you have this wobbly, excited droplet, and it gets so excited that it breaks apart, and it not only breaks apart into 5 pieces, so it splits and forms 2 new elements, and it also generates more neutrons. And then those neutrons are free to go and absorb other nuclei, absorbed by other nuclei, and then they can go on. And this is known as a nuclear chain reaction. So, and believe it or not, this is a natural occurrence. There's something called the Okolo furnace in Africa. So there was this deposit of uranium in Africa, and they found out that there was a little less uranium-235. There tends to be 0.7% uranium-235 in the uranium that we get, and we dig it from the ground. The Okolo furnace had much less, and like, this is weird. Why does this uranium have less? And then they figured out that what happened was over periods of rain, and I mean, back in the past, there was more uranium-235. It also decays faster. It has a shorter half-life, and water would form over, just by rains, would form over this uranium deposit, and then the water would act as what's called a moderator. It slows down neutrons, and it created a nuclear reactor. So it was a natural nuclear reactor, and it would turn off and on. And so we've seen this happen. So of course, we do this ourselves for nuclear power. And so let me go down here to briefly talk about this. So soon we're going to talk about the nuclear binding energy. And this plot here, binding energy on the y-axis, x-axis is mass number. And generally speaking, so as things start out light, like hydrogen, and nuclear fusion dominates till you get to iron. The most stable nucleus is iron. And then after iron, it actually, fusion becomes endothermic. And then, so nuclear fission for things beyond iron is exothermic. Nuclear fusion for things lighter than iron is exothermic. So nuclear power, we tend to use uranium and or plutonium, because plutonium transmutates, it forms from uranium. So you can form plutonium. So if uranium-238, uranium absorbs a neutron, I don't want to write all the equations. So it absorbs a neutron, it becomes uranium-239. And then this beta decays to neptunium-239. And then this beta decays to plutonium-239, 92. So and this also is what we use for nuclear weapons usually. So one of the problems with nuclear reactors, well, good and bad, the plutonium continues to absorb neutrons. and it can get as high as 242 plutonium. And that's more stable because it's an odd number. Even numbers are less. I'm sorry, it's an even number. Odd numbers are more unstable. So plutonium 239 is unstable, but it forms first. And that is by far, that is way better than uranium for nuclear weapons. And you can use plutonium 241, but the problem with plutonium 241 is that you also have plutonium 240 and your plutonium 239, so it's hard to isolate. So it's almost always 239 plutonium for nuclear weapons. So, but okay, let's go to nuclear power plants though. And there's a bit of history in nuclear power plants. The Navy vessels tend to use this setup. And here in the United States, well, I think it's 106 now. We used to have 110. Now we just decommissioned them. We have 106 or so nuclear reactors, and we have 106 different nuclear reactor designs. We don't have any set designs. Other countries, so France, Lithuania, they have more of a standardized nuclear reactor design. We don't. And we have a couple different types. This is a common one. So the nuclear reactor, you have the reactor core here. And so in the reactor core, you have what they call the pile. So this right here, this is known as the pile. And where a lot of these terms come from is actually from Fermilab, the original nuclear reactor. So the original nuclear reactor was in Argonne National Lab. They actually built it in a stadium. And the pile was literally a pile of uranium oxide. They took uranium oxide, made it into hockey pucks, and they piled it up. And then they had the control rods, which were more or less like 2x4s with beryllium like duct tape to it, or like athletic tape, and they would raise it up and down. And so here the control, what do the control rods do? The control rods absorb neutrons. So, and they had a guy with an axe standing by the wall. So just imagine this guy with an axe by the wall, and there's a rope tied to it. And over the nuclear reactor, that's just a pile of uranium oxide, and you can, this wooden, structure tied to a rope, in a pulley system, just waiting. And if they said, shut it off, the guy with the axe would hit the rope with an axe, and then, thing would fall down. So in a nuclear power plant, when you say axe, it means drop the control rods. So, and things are designed, these nuclear reactors are designed such that if there's ever a power failure, the control rods go down. So, and what does that do? That stops the nuclear chain reaction. So then when the control rods are down, the nuclear reactor is off. So when the nuclear reactor is on, or in general, it is generating heat. And another thing to say, that like with the Japan Fukushima event, the reactor turned off. So, but another thing though is that when things are radioactive, another word for radioactive is hot. Like if you say this thing is hot in a nuclear sense, it means it's radioactive. And things that are radioactive, among other things, they are literally hot. They generate heat. So and that heat then though, if you have say like a bunch of nuclear materials contained in something, and you have water, if you heat it up enough, the water will vaporize, and then heat it up enough, the water will turn into hydrogen and oxygen, and then it'll explode. So if you have a system that just, contained with water, and you have a heat source that is continually pushing off heat, like something that's radioactive, give it some time, it will explode, unless you find a way to vent it. So, but anyways, coming back to a nuclear reactor, and the other thing about nuclear reactors, we don't heat them up, at least in the United States, we don't heat them up very hot. So meaning that the temperature of a nuclear reactor is about 500 degrees Celsius. And a candle flame is around 550 to 600 degrees Celsius. So a candle flame is hotter temperature-wise than a nuclear reactor. So we actually keep our nuclear reactors here in the United States pretty cold. So why? Because it's safer. So this is known as a pressurized water reactor. So in a pressurized water reactor, you have the nuclear core here, and you use water to heat up that takes the heat from the nuclear reactor, and then it goes through a heat exchanger, and then you boil water here in the heat exchanger, and then it goes back into the core. So you contain the water. And the other thing about nuclear reactors here in the United States, we only use what's known as saturated or wet steam. We do not superheat the steam. So it makes the turbines, they're less efficient. And the other thing about them is that water condenses on the turbines when they spin. So it leads to, they don't last as long. So we don't, but like I said, we don't superheat our steam for any of our designs because we like to keep the nuclear reactor cold. So we don't like to heat up our steam very much. There's other types of reactors. You can have what's called a boiling water reactor, where you have the core and then it generates steam. And then, so it's like if you have the core here and then the steam comes up and then the steam turns the turbine. That's a boiling water reactor. So like I said, we have 106 nuclear plants and we have 106 different designs. We don't have a standard one. And well, the nice thing about nuclear power is it generates a lot of energy very cheaply. The bad thing is it makes radioactive waste. So you generate about a car sized. So each of the nuclear plants that we use, they generate about about the size of a car, like a compact car amount of nuclear waste a year. This stuff is hot, it's radioactive. So they have to sit it and they have to cool. And so they have cooling stations. And if you don't keep it cold, it's going to blow up. So that's one of the problems with nuclear power, right? So it's difficult that way. And well, what's also interesting, different designs. So Canada has nuclear power plants. They have what are called heavy water reactors. Here in the United States, we use what are called light water reactors. This water that's in this water bottle, this is light water. It's mostly hydrogen, the protium hydrogen versus heavy hydrogen, which is deuterium. So these are light water reactors in the United States. Canada uses heavy water. What's nice about heavy water reactors is you don't have to enrich the uranium. So I told you dig uranium from the ground, it's 0.7% uranium-235 and in Canada, you can just throw that, you can just isolate the uranium and throw it into a nuclear power plant and it works. Here in the United States, we have to enrich the uranium to somewhere between 3 and 9%. So, and for applications, if you know what's going on with Iran, so Iran is saying like, oh, we're using our nuclear, we're making uranium for purely peaceful purposes. We're to use it for nuclear power. And we're saying, well, we're finding enriched uranium past 20%. And Iran's like, don't worry, civilian use. So one thing about, like I said with nuclear power plants, we like to keep them cold. So if you enrich the uranium past, well, even 9%, so if it's enriched past 20%, you get a hotter nuclear reactor, right? You get means this core is hotter. It's going to get hotter than 500 degrees Celsius, which means you have to have a bigger system to just displace this heat. Because if you have a hot core, what's going to happen? It can explode. Well, I mean, it's not going to nuclear detonate explode, not at this concentration, but it's not going to, it's just going to be, it's going to be harder to work with. It's going to be more expensive, and it's not going to, there's no benefit. So the idea is either Iran is galactically stupid and they hate money, or they're making nuclear weapons. So that's like the whole, that's the fight that's going on there. It's, do we have applications where you super enrich uranium? Yes. Yes, you do it when space is an issue. So in a nuclear sub, nuclear core is on the size of liters. So it's not very big. So because space is premium on a sub. In a civilian power plant, the core is probably going to be about 2 to 4 times the size of this desk in the front of the classroom. So, but why, it's either, you have a core the size of this water bottle-ish, or a core the size of the desk. Like, it's way harder to control the nuclear reactor in this core. It's much more dangerous, much more likely to explode, so many things. Why would you do it? Space. And it's harder to make the materials too. The desk, size nuclear reactor core is way more cost effective, and it's safer. So yeah, why wouldn't you do it that way? So, but yeah, that's a nuclear reactor. And also, we in the United States, we do not reprocess our control rods. Other countries do it. When you reprocess your control rods, the fuel rods, excuse me. You reprocess the fuel. What are you doing? You're isolating plutonium. And you can use plutonium. They do this in Russia. They call it mixed oxide fuel. And it's plutonium and uranium mixed together. So, it runs for a while. And we don't in the United States, just because we want to try and say, like, nobody makes nuclear weapons. So, except for us. Right. But we apparently don't make them anymore. But other countries do it, but we don't. So, okay. And okay, well, let me talk about the binding energy then. So it's kind of hard to talk about this without talking about the binding energy. So I'm sure you're familiar with this equation. E equals mc squared. Energy is equal to mass times the speed of light squared. So the idea with that is a little bit of matter has a lot of energy. And so, and I didn't bring this book. I should, if anyone wants to see it, I have a book that has the masses of every single nucleotide. So at least the ones we know of, it tells its half-life, it tells its spin, it tells its mass. And the idea with this is kind of going on this chart. Sorry, I'm jumping back and forth, but protons and neutrons change their mass depending on which nucleus they're in. And protons and neutrons, as they approach, generally speaking, as they approach iron, iron actually has the lightest nucleus. So in terms of protons and neutrons, so the protons and neutrons in iron are the lightest. And then after iron, the protons and neutrons start to become more massive. So, and you can see how much mass it's losing by something called the mass defect. So at least we call it the mass defect. So if you look at this, what is the binding energy per nucleon in mega electron volts for carbon-16, an isotope of carbon that has this mass, 16.014701 AMU atomic mass units. So how are we going to figure out the mass defect? We're going to take the mass of a proton and the mass, well, it's so carbon 616. This is going to have 6 protons plus 10 neutrons. So 6 times the mass of a proton plus 10 times the mass of a neutron, a neutron and a proton, not in a nucleus. And then we're going to subtract the mass of this carbon-16. That tells us how much mass is missing. So when if you were to take 6 protons and 10 neutrons and stick them together, forming carbon-16, what's going to happen is that carbon-16 is going to lose 0.11 whatever, mass, atomic mass units. So you can do this in one of two ways. You can do the equals mc squared way. To do that, though, you'd have to multiply. If you want to do that, you have to multiply it from atomic mass units to moles, and you have to convert to. You can do it per moles, but for here, you can use this ratio that there is 931.5 mega electron volts per AMU. What is an electron volt? So this is from it comes from the cathode rays. So if you have an electron and you put a potential of 1 volt, so if you have an electron in a tube and you have 2 plates and you charge the plate with a voltage of 1 volt, so 1 volt with an electron, the electron gets shot out of the tube with a kinetic energy of 1 electron volt. So that's where the unit of electron volt comes from. It comes from the energy, the kinetic energy the electron has from a cathode ray. So if you have put 1,000 volts on this, the electron has 1,000 electron volts. So this ratio here is mega electron volts, mega being 10 to the 6 electron volts, so 1 million electron volts. And which means that this carbon-16 releases the energy of 110.74 mega electron volts. So let's see here. I guess if you convert this to joules, so let's say if you were to say if you had a mole of this, so if you have 110.74, I guess I don't have enough sig figs. 110 mega electron volts times 10 to the 6 EV for MeV times 1.6 times 10 to the minus 19 joules. Oh, I'm running out of space. I'm just doing this to give you an idea of how much energy is in nuclear reactions. Joules per EV, then times a mole. So let me do this in my calculator. Okay, of course, my free calculator app always makes me look at an ad. So 110 times a million, 2, 3, 1, 2, 3, times 1.6 minus 19 times 6.02 E23. So this is 1, 2, 3. Ooh, there's my ad. Ooh, you can open a bank account and get a $500. Did you know that, class? 1, 2, 3, 4. This is 10. This is 10 to the 13 joules. So 1 mole. So 16 grams of this stuff releases 10 to the 13 joules of energy. And I don't know what the oxidation of sugar is. Sorry, I should have, I was gonna do this, I should have done it, I should have prepped it before class. You can see me think in real time. So where's glucose? So glucose. Actually, no, that's supposed to be the what's something to, I guess I don't, if you compare it to something like burning, it's going to be, it's massive. I have to look to, do you want me to compare it to something, or are you cool with the numbers? You want to, okay. You want to compare it? Okay. Or am I reading your facial expression right? You want to compare it? Okay. Oh, we got a request to compare. Let's see here. Which chapter was it that did thermo? Was it 14B? No, it wasn't this one. Where's the one I was burning something? I'm trying to see if I have a problem. I was burning something. Okay, when you compare it to the heat of vaporization. So heat of vaporization for water is 40.7 kilojoules per mole. So this is going to be, so heat of vaporization of water is 40.7, right? So 40 times 10. So water is 4 times 10 to the 7. So to take a mole, 18 grams of water and boil it, it is, it's whatever, 40,000 joules. So compare that to 10 to the 13. So it's a difference of 10 to the 6. So 5. So it'd be like, let's see here. That'll be 500,000. So that means I'm just kind of, that means the energy released in taking 16 grams of carbon 16 is the same amount of energy that you could vaporize 500,000 moles of water, which, 18 grams per mole, so it'd be like times 20. So that's going to be 2 million grams of water, which would be 20,000 tons. So 16 grams of carbon forming, just releasing a little bit of energy, it would release the same amount of energy that you could boil 20,000 tons of water. So there's a, a reference. So that's a lot of energy, right? 20,000 tons of water from 16 grams. So that's why, like, nuclear power and nuclear weapons are scary. Well, nuclear weapons. But also coming back to this, the curve of binary energy, if you look at these, right, if you look at this binary energy, I mean, right away you notice this curve is a lot steeper than that curve, right? So nuclear fusion, there's a lot more energy in nuclear fusion than there is in nuclear fission. And surprise, surprise, I'm sure everyone knows this, that's how stars get their energy. Stars get their energy from, like, our sun takes hydrogen and turns into helium. The sun is actually known as a carbon-12 star. It uses a catalyst. It takes carbon-12, it makes nitrogen and oxygen, and then actually oxygen then emits helium and goes back to carbon-12. So actually there's nuclear catalysts that can happen. So we actually can have the different nuclear reactions that happen. So, but you can see here fission, this end, like going from uranium to splitting uranium, you get, you can get this much energy, but then you go hydrogen down here to helium, right? That's going to be that much energy. So fusion generates much more energy than fission, generally speaking. So, and when it comes to nuclear weapons, that's why there's certain type of nuclear weapon called a thermonuclear weapon, where you actually have a fission bomb. So you have uranium or plutonium that gives the activation energy to give a nuclear fusion reaction, and then that's an even bigger yield. So you can have really, really big yields. So yield being explosive power. And well, I mean, that's what we use fusion for weapons, but we're trying to turn it into something peaceful. And we have two ways of doing nuclear fusion. One of them here, this is the Russian design. This is known as a tokamak. It's kind of like this donut. Have you ever seen the original Iron Man? That's what that's what inspired the whatever it is, the arc reactor, whatever they call it. It's inspired off a tokamak. And the idea is here in the tokamak, you really excite the plasma, so it's going to be hydrogen, and you slam it together, and if you heat it up hot enough, you can form nuclear fusion. So why is this important? So protons are positively charged. You take two protons and you're trying to push them together, they're going to repel. So you have to really push them together until the nuclear strong force will overcome the electrostatic repulsion. So you have to really, really hit it hard. And not only that, for a reactor like this, you have to wait until there's 4 protons. So you have to take 4 protons and slam them together at the same time. So it's really hard to do. And it's easy to do in a star, because in a star you have gravity. So it's just a big massive star, and in the center of the star, the gravity is stronger. So just by gravity pulls enough energy to overcome the electrostatic repulsion, and then has nuclear fusion, and that generates energy. So then the nuclear fusion pushes out and makes the star, it expands the star, and then gravity pulls it back in, causes the hydrogen to fuse, which expands the star. So stars they tend to have this equilibrium between their gravity and then the nuclear reactions, keeping it from compressing down to depends on how big the star is, to a neutron star or a black hole, which is a neutron star. So, that's one way to do it, is a tokamak reactor. We are doing research in the National Ignition Facility in Lawrence Livermore. This is not in the textbook either. What they do is they take a pill about the size of like a vitamin tablet, and they hit it with a bunch of lasers. So they focus down a bunch of lasers, and this vaporizes the surface, which compresses the inside. And it compresses the inside to the point that nuclear fusion can happen. And they have it work. It's working right now. Just like the tokamak, though, they do not have a net energy positive, net energy positive event yet. Tokamak, the people that work on them, they say it's like, imagine weaving a basket made of Twizzlers that will hold water, is what they said. It's because trying to get the magnetic fields in a tokamak to align and get it, and that's how they get the stuff to speed up. So temperature is kinetic energy, so they use magnetic fields to spin hydrogen or whatever around. So they can get to work, but it's energy negative, meaning they get more energy, they put in more energy than they get out. Same thing with the National Ignition Facility. Great news was they got it to 60% recently, so we're getting better. But this is more research. I mean, it's kind of like it's hard to do. I mean, at least for now, we haven't figured out everything yet. But it's almost like I can imagine like shooting a shotgun kind of thing. Like you have a bullet and you fire it, and it's a lot of energy. Same idea. You would have like a machine that you put in the pellets, and then you hit it with lasers and it explodes. And generates a nuclear fusion. So then that energy is released. So okay, so other things. So just mentioned for nuclear. So if you ever wondered what an accelerator is, sorry, I like this stuff. I'm thinking at a time. I'm talking a lot about this stuff. So SLAC, the Stanford Linear Accelerator, that works by taking protons, and this is how you can shoot things. So this is a diagram showing like a linear accelerator, and you take a charged particle like a proton or an electron, and it emits, and then it goes along these different stages. You can see the stages get longer, and if an alternating voltage source, because it goes positive and negative, they charge positive and negative, and when it's charged positive, if you have two plates and it's charged positive and you have a positive charge, what actually happens is it ends up accelerating it forward. So you can accelerate particles this way. We do it cathode ray too. It's electrons. You need protons for an accelerator, and then it shoots it along. And if you want, you can put magnets here. You can put a magnet here and it'll bend whatever it is. That's how television works. And you can do the similar thing to put it into what's known as a cyclotron. So this is a cyclotron, and you can either just have usually you have a linear accelerator shoot into a cyclotron, and then by changing the frequency of positive and negative, the whatever charged particle spins around, and then you can shoot it out. So that's if you ever wonder what a cyclotron was, it's going to be a linear accelerator that's attached to a cyclotron. Well, it generates protons or whatever. You can look at other things too, meaning like lead nuclei or something. So, and then you can accelerate things. These are particle accelerators. And then what do you do with these particles when you accelerate them? You can smash them into other things. So you can make super heavy elements. So many of these elements, so if you look at the periodic table, so like these elements here, they are all pretty much made in cyclotrons. You can get, so where do the elements come from? So these elements, so the Big Bang happened. Hydrogen was primarily formed from the Big Bang, formed a little bit of helium, lithium, and beryllium. So depending on the source of beryllium, then stars will make it up. Our sun will not make really anything past carbon. So stars 3 times or more massive of the sun can make iron, and if a star is massive enough to make iron, you can get what's called a type 2A supernova, where the core of the star starts making iron, and when that happens, fusion is endothermic. Gases, when it's endothermic, it shrinks, so the core can shrink really fast. That implodes, causes a shock wave for an explosion, and then the star just lights up. And then you can make, with that, you make many of these other elements. Some of the elements are also made by collision of neutron stars. So for a star 3 times or more the mass of the sun, you can get something called a pulsar, where the leftover remnants of the star, its gravitation is so strong that that the protons and electrons turn into neutrons, and you have it's a star that's just made of it's like a big nucleus made of neutrons, and then it spins really fast just by conservation of angular momentum, right? So maybe you've seen like this, and if you turn your the whole, if you, I don't know if you studied it in physics, where this is slow and you turn your arms in, you spin faster. Same idea, but really, really fast. So that's a pulsar. And if they collide, you can form the other elements. We've made some of these from nuclear bombs. So we discovered them from nuclear detonations. These here, though, these are only going to be man-made, because you have to really slow down. You can only make them in a cyclotron, because you have to take the nuclei. Remember, nuclei are like droplets. You have to have them cold, meaning they have to be very unexcited. Sometimes to take them, you have to wait for them to emit gamma rays and make them more stable, and then collide them with other ones. So, okay, how are we doing for time? 10 minutes. So let's talk about radiation. How are we doing? Sorry, anybody have any questions? Sorry, I'm getting excited talking about everything that's not outside of the book. So what about radiation? A unit that's oftentimes used is a rad or a rem. It'll be about the same for everything included. For all intents and purposes, they're the same thing. A rem deals with the biological activity. A rad just deals with the number of events. And so, but this is what people normally get. So one of the places you can get radiation is actually from riding a jet. And this only works during the day. At night, you don't get as much radiation because the sun's not shining. Right, so a 5-hour jet plane ride, you get 2.5 millirem. So cosmic radiation, so we're being hit by radiation, we get 27 millirem. And so I guess I should mention what the effects of the REM are first. So in the United States, we're allowed to get 5 REM. So the average person get 5 REM. You can get a permit to get 10 REM. So, but you don't notice any physiological effect for radiation until you reach about 20 or even 25. What happens then is that you get your blood cells change a little bit, and then you get maybe a slightly higher cancer risk. At about 100 REM, you can get radiation sickness. What is radiation sickness? It's kind of like having the flu. I've never had it, but it's going to be similar to a bad case of the flu, meaning you'll feel achy. You might get skin lesions. You don't get that with the flu, but you might throw up. So I think your radiation affects your eyes, your hair, and your stomach more, because those cells reproduce more quickly. So your hair can fall out at about 60 rem. Depends on the person, but at the dosage of 60 rem, your hair can start to fall out. So higher than that, higher than 400, then you can have death. Depends on your dosage and your time. So and so what are our dosage? And this is millirem, so this is 1,000th of a rem. So, and the on average, though, people maybe get 100 to 200 millirem a year. I mean, it's not much. So, and for us in Hawaii, we don't have a radon source. So actually our background here is lower. So, I mean, so what other things we have? The Earth is slightly radioactive. There's radionucleotides in our body, carbon 14 already mentioned, potassium 40. Other things, so if you get a chest x-ray, that's 8 millirem. I'm not afraid of x-rays, so it doesn't bother me when I have to get an x-ray at the doctor. So, dental x-rays are a little stronger. That still doesn't bother me. I don't have to worry about a mammogram because I'm male. So if you, this may be a little out of date. So I have gotten this. I've had two of these. Well, I guess that they're CT scans. I had the abdomen CT scan, and my dose was 1.7 rem. I got a CT scan. I was just I asked, hey, can I know what my dose was? And they gave it to me, and I calculated it down. They gave it to me in grays, and then I calculated a rem, and I was like, wow. So I mean, like in about 30 seconds, I got 1.7 rem, which is fine. I mean, obviously they're not going to kill me, but we're allowed to have, like I said, we're allowed to have 5 rem a year. So other things though, smokers can get 16 rem from the cigarettes. So if you get a pack a day, means 16 rem to your lungs. So that's a pretty hefty radiation dose. I mean, it's not the end of the world, but it is within this range. So, but the point of this though is that by far most humans we get our dosage from natural sources. To give you an idea though, in the Fukushima event, the workers there, and they were there for several months, and they got about 25 rem. So people were upset, and they're like, oh, we're gonna stick this out, and like I said, they got 25 rem. So they're I mean, they're starting to show physiological effects, but they're gonna be fine with 25 rem. Whereas the people in Chernobyl, they were hit with a much higher amount, or people that are around nuclear weapons, much higher. So, and so radio tracers. So what are the things we do with radioactivity? So I've had this happen to me twice, the technetium-99. I've done a bone scan. They were looking for stress fractures from an injury. And I think I told you guys last class, I ate a radioactive sandwich once. They did a stomach emptying study. I had a doctor that thought I had a condition called gastrophoresis, and that means that your stomach doesn't empty as rapidly. And actually my test turned out that my stomach empties faster than normal, but not dangerous kind of thing. So the doctor was dead wrong. So, but technetium-99, it's a synthetically made element, and after it's made, it's excited, and it emits. So the excited nucleus, it emits gamma rays. It has a half-life of 6 hours. So you can do that. Maybe I'm showing my age. The band called The Offspring, they had a album cover. It was a bone scan image. And you can do things with just tracking where things are. You can do with radioactivity. Iodine-131, this is, use it to image your thyroid. So right here, you can use it to image your thyroid. You can also use it to kill your thyroid. So people that have Graves or Hashimoto's disease, frequently you can take iodine-131 and it can just irradiate the heck out of your thyroid and can just destroy it. And well, I haven't had it happen to me, but I know people that have, and you have to go on an iodine-free diet before you do it. And it's amazing how hard that is. You basically eat fruit and meat. That's the only thing you can really eat. Anything dairy, you can't eat. So iron, and so what am I talking about this? You can do imaging. So like, I wanted to figure out how fast my stomach empties, and like one of the ways you could do that is real easy. I ate a sandwich that had technetium-99 in it, and then it was a kind of a boring day. I said, let's hang out in the hospital, and then every half an hour or so I had to go. They had this machine. I just stood there, and they let me sit there for 3 minutes, and they said, all right, done. And like, all right, That's my shut up alarm. All right, I'll tell the stories later. I meant to finish today, but I got so excited talking about stuff. Do you guys want to learn about nuclear weapons or you don't care? Nope. Okay. I don't know. You can ask me next time if you want to learn about nukes, but I'm almost done there. I'll finish up real fast and then I'll start doing review for the final. I know, yes, I shouldn't apologize for being excited, but I love this stuff.